Okay. Hello everyone. My name is Chinmay. I've been for the last 2 years now at the University of Washington, and yeah, it's thank you so much for having me. Um, as Atul said a second ago, it sounds like there's been some interest in these problems that lie in the difference between the complexity classes QMA and QCMA. And what I'd like to do is I'd like to spend some time today sort of explaining how one might hope to understand this separation a little better. In particular, how one might try to prove an oracle separation between them, and introduce you to a paradigm of converting uh, um, uh, classical advice or witnesses into samplers, and then arguing results about that. So to begin, this talk is going to be situated in the space of quantum complexity theory. So as a consequence, it might be just good to have a little bit of a reminder of some ways to think about complexity classes. Now, complexity classes, of course, they are collections of problems that can all be solved by the same protocol nature. In this case, we might start with the classes NP and MA. These are classical complexity classes. And they're defined in the following way. You imagine an interaction between two computational devices. It's um, it's probably just fun to anthropomorphize these devices and give them names. And traditionally, we call the two devices Merlin and Arthur. Now, the way you should remember this is Merlin. I tend to draw Merlin just by a hat. I'm not very good at drawing faces. So I draw just the magician's hat, and Merlin is an unbounded computational device. He can solve any problem he wants, but he's untrusted. Meaning you need to actually be certain if you ask him to solve some question, whether or not it's true. So you could ask Merlin a question like, does this machine halt? Merlin might say yes or no, but of course you can't trust it. So the caveat of not being able to trust whatever Merlin says is the only limitation that the computational power has. Um, the second player in this game is Arthur. Arthur is a device, he's a polynomial time device, and he's interested in some question like is X in a language, right? Any traditional complexity problem, we can just think of in this manner. So for now, we'll just worry just about decision problems. And the interaction that defines NP-RMA is defined when the interaction is a classical message and Arthur is a classical computer. Of course, the class NP-RMA has a natural complete problem, which is three SAT or three color. There's actually many complete problems that define this. So all problems are morally, in some sense, like solving a SAT formula. Let's elevate these complexity classes to some quantum notion. And the first way we could elevate this is we could ask that Arthur no longer is Arthur of today, but maybe Arthur of 100 years from today. He's a polynomial time quantum computer. And so now Merlin's, let's assume the message system that Merlin and Arthur interact over is a classical single round classical message. This brings us to a class quantum classical Merlin Arthur, or also known as QCMA for short, where now messages sent are quantum, but Arthur is able to interpret the quantum messages with a quantum computer. This class is necessarily more powerful than QMA because, than NP or MA, because Arthur can always simulate a weaker device. We lastly lifted to the following class, QMA, where now we assume that the interaction allows for sending of quantum messages. This class will be bigger than QCMA, and we have a nice containment of these classes from left to right of increasing power. The real question we are interested in is whether or not any of these containments are strict, whether or not there's a dramatic increase in power that we can provably argue. Now, to start looking at this question, we have to recognize that although I've only listed 3 complexity classes on this page, there are actually two other pertinent complexity classes we should be aware of. And those are the complexity classes of P and P space, polynomial time classical computation and polynomial space classical computation. And the interesting thing is that these three classes are sandwiched in between P and P space. And it's been open for 70 years or so, whether or not P and P space are actually equal. So in fact, what this argues is that any separation between these complexity classes at all would also imply a separation between P and P space. And we do not really believe that we have the techniques for doing so, although it's entirely possible that something of this nature could be the reason why we separate P and P space. But what we're going to focus on in this lecture is we're going to specifically focus on trying to separate the classes QMA and QCMA and argue what might be the reason to believe that these classes are actually separate and what might be the reasons why they might be the same. Okay, before we do that, let's take a brief moment and just think about why we should care about these classes at all. What is this question in complexity theory saying about the real world? So one way to start is to recall that there's a very pertinent complete problem for the complexity class QMA, meaning it's the hardest problem in QMA, and that being the local Hamiltonian problem. It's a natural quantum analog of constraint satisfaction problems, which are NP complete, and therefore it, as the hardest class, any problem in QMA is morally representable as a local Hamiltonian problem. And furthermore, it captures many natural problems from physics and chemistry. And so in some sense, it's not exactly correct, but I think it's reasonable, at least for the sake of inspiration, to say that solving QMA complete problems is tantamount to being able to compute all the relevant properties of local Hamiltonian ground states. And just for a reminder, the local Hamiltonian problem is the problem of estimating the ground energy of a local Hamiltonian system. So what does this say? It says two things. It says, well, one, if the two classes, if QCMA equaled QMA, then there would exist a classical description of ground states that captures all the relevant properties. Meaning we could always find someone could always give you a classical description for every Hamiltonian you're interested in. And from that classical description, you could derive all the classical relevant properties that you might be interested in by just formulating that problem as some problem in QMA and then applying whatever reduction you have to equate the classes. The alternative is that if the classes are not equal, then you have that provably not all local Hamiltonian ground states have efficient verifiable descriptions, meaning that there are these local Hamiltonians which fall in this very peculiar space where you can't detect the you can only detect whether you have found the ground state. You would never be able to describe it. They almost feel like art. You could never recreate it yourself. But when you see it and you're like, oh my goodness, it's beautiful, right? It's a sort of a very peculiar phenomenon, which almost entirely, in my opinion, we have seen in like literature and other sort of such fields, in the humanities. But now we have a sort of a mathematically description of such an object, and we're trying to ascertain it. Okay. Another way of saying this is imagine the following situation occurs. To say you have Arthur, he's a polynomial time quantum computer, and he wants to understand a ground state psi of a local Hamiltonian system. And even if he has a copy of psi on his quantum computer, assuming something like BQP does not equal QCMA, which is a fine assumption, I think, to make, we have that Arthur is not able to write down a description of psi, even if he has psi in his lab, meaning that he's kind of stuck just with the one copy of the state he has. He can't really do anything with it otherwise. Okay. But on the other hand, let's assume that QCMA equals QMA. In this world, Merlin is at least potentially able to write down some classical message about psi, which he could pass on to Arthur, and then Arthur could use to verify properties of the Hamiltonian system that he's interested in studying. So turns out, right, that somehow the description is there, and it's just that someone had to spend some time finding it. But once the description's found, he could send it to Arthur. The best part about this is Arthur can then go on and forward that classical description to all of his friends, and everyone else can also verify properties about the Hamiltonian just because the classical message itself is uh, easily copyable and transferable. However, in the world that the two classes are not equal, it's the issues that Merlin can struggles to write down a description of the state that Arthur is able to understand. Any description that he's able to write down, either Arthur cannot trust or it's too complex, meaning that the state psi can be verified but not described. And so then the only hope for Arthur is if Merlin sends him a copy of psi, which he'll be able to verify and then not write a description of. And then if Arthur wants to then tell his friends about the state, the only thing he could hope to do is send them a copy of the state. He's stuck with the fact that he has only one copy of the state and he can't do anything else with it. How does that? Any questions so far? How's everyone doing? Could I, out of curiosity, it's more helpful for me if I can see everyone's faces. Would it be all right if I request that everyone has their video? That way, at least, I mean, since there's only 4 people here. Um,
There's actually about 10 people.
oh, there are 10
But
people. Oh,
yeah.
I see. I only see 4. I'm so sorry. Okay. Oh,
No,
okay. Then, yeah.
no,
It's always nicer if I can see more faces, so I can, especially with these online talks, it's hard to gauge if I'm just droning on. Um, Okay. Um, okay. Uh, all right. Um, okay. So what would we like to do? We would love to resolve which of these two worlds we're in. We want to understand if we're in the world where QMA equals QCMA or if they're distinctly different. Now, as I said before, we won't be able to prove this problem outright because of this PP space issue. However, what we can do is we can do the following. We can identify a property testing problem for which the variance QMA and QCMA are indeed not equal. And what we can do with that is that once you have a property testing problem, you can lift that to say that with respect to some classical oracle, these complexity classes are indeed not equal. So let me just say a brief history of this problem of trying to separate these classes, either by property testing or oracle. It turned out to be equivalent. This line of work started in 2006. Aronson and Kuperberg first proved that this is true with what's called a quantum oracle separation. So it's a property testing problem about unitaries. In that world, you have some unitaries that you get to make query access to. However, you don't get to see the internal structure of the unitary, and you're trying to decide some property of the unitaries. It turns out that there's a property that is verifiable with access to a quantum witness that's not verifiable with access to a classical witness. This is what lifted by a few results in the middle um, uh, that tried to take inspiration from the Aronson-Kuperberg problem to try to create a classical witness for this problem. And they sort of pecked away at this, including work of my own, by simplifying the sort of assumptions we make on the device or reducing the quantumness of the oracle. But the issue of trying to construct a truly classical oracle separation or a classical property testing problem eluded us. A work by Liu, Mukherjee, and Yuan actually proved that there is a conjecture in pseudorandomness which implies a oracle separation, a classical oracle separation between these complexity classes. And this problem corresponded to this some sort of set size estimation for an expander graph. Um, And what we'll show you is in this work, we'll show how we can uh, construct a true classical oracle separation between these complexity classes. And the computational task we'll consider is the task of estimating the spectral correlation between two subsets, given which will give us a classical separation. I should say that after this work came out, there was a follow-up work which I believe you guys had the chance of hearing about, uh, which constructed a QMA versus QCMA separation based on the Yamakawa-Zandri's verifiable quantum advantage with structure result. And it's built on a similar set of techniques of using a sampler, and then it's built on some nice construction of very good classical error correcting codes. Um, uh, it's really nice that they're now in a short span two different computational tasks that construct an oracle separation. I think they're both intriguing on their own accord. And it's just really nice that there's multiple ways to solve a similar problem. Um, the task I'll show you is one that's a little bit more compressed Oracle-like and more, I think, pertinent to tools from cryptography. But then there's also this other alternative procedure, an attack based on error correction. Okay.
So can I ask a small question? Oh, okay, go ahead, Alex. Yeah.
So just like a tiny question. So can I ask what is the difference between your result from 2022 and the Henry's result from 2025? Because they seem to both rely on this size estimation of an expander graph. Is it like the same problem, but you kind of like deal with it from two different angles, or?
No, it is so. It's the oracle is exactly the same. The attempt is what is the proof technique to prove the QCMA lower bound. What happened in the work by Liu, Maturja, and Yuan is they identified a pseudo-randomness conjecture, which argues a significant structure on what the classical witness could look like. What they argue morally is that assuming the pseudo-randomness conjecture is true, we can sort of break up the witness into two halves. One half, which is the useful parts of the witness, and the other half, which is the useless parts of the witness. The useful things are parts of the witness that Arthur might be able to interact with, might be able to verify. It could be something like the witness says there is an edge between vertices 12 and 18 or something of this nature. Something which Arthur could look at and be like, oh yeah, no, I see that. That makes sense. And the parts of the witness that are that Arthur would find useless. And this quantification of parts of the witness that are useful or useless is interesting, and is part of the technical challenges, constructing the classical oracle separation. So both my work with Anand in 2022 and the following work attempted to deal with sort of this classification of useful versus useless parts of the witness. We argued that in a distribution testing problem, you could argue that by hiding stuff in a little bit of a distribution, you could argue that there could be no useless parts of the witness, and therefore you had an oracle separation. What Liu, Maturja, and Yuan do is they argued that assuming the pseudo-randomness conjecture, the useless parts of the witness are indistinguishable from true randomness to Arthur, and therefore you still have the separation. So there were two different ways of arguing that any part of the proof could be separated into useful and useless, and then the useful part was actually not strong enough, and the useless part is thrown away.
And just to make sure I understood, so you are quantifying like the useful information of the witness that would essentially correspond to, let's say, classical queries to the underlying oracle that you are considering? Like, can you show
Yeah.
that that's kind of like the best you can contain in a witness, that the most useful information you could contain actually just corresponds to a bunch of classical queries to this oracle that you are constructing?
Yeah, that's a great question. I mean, in some sense, what we can argue is that if the witness only told you things about the graph that you could have found out on your own through queries, then that's what we call, that's what I'm colloquially calling useful. But the challenge is to say that there is not some side information about the global structure that Arthur himself could not construct, but it could be verified, that could be told to him. And that's the inherent challenge. What we'll show today is a different way to get around this, because we'll show that we just want to argue that no matter what no matter what type of information is told, there's some bound as to the amount of information that can be held in a classical message.
Right, this is like the fact we'll use like the compressed oracle just to
Exactly. Yeah.
I see.
Yeah. Let's how about we keep going, because although those papers are interesting, they're not related to the at least the separation I'd like to talk about today.
Yeah, so let's talk about this. Yeah.
Okay. Any other question? I thought you might have had one.
I did, and I think I forgot. I'll ask you later. Sorry, please. Uh-oh, we lost the slides.
Okay. Yeah. Just give me 1 second. I'm trying to move this thing up because I can only see 2 participants. Is there a way I can? I would like to see at least more faces. I only see Atul, so it's very hard to tell.
I think some of those 3 buttons, and I think one of the buttons in the preview would allow you to see more, I think.
Yeah,
And
it shows me some names of people who have their cameras off, which is not very helpful.
Oh.
It's
maybe if you click on people, does it?
I think if you press more, maybe there's an option to hide people without videos.
Yeah.
Does it have any
Settings? No, it doesn't. Okay.
I'm sorry. Yeah, it's
Yeah.
just Teams
It's
being
okay.
Teams.
No, okay, it's fine.
I'm sorry.
Yeah.
Oh, I think you can go full screen and then it'll show other people's. It'll change.
Okay, there. Yeah. Actually, once you started talking, you showed up. If everyone who's off has their video on, if they could talk that way, that would just help me so much. Just say hello.
Hello.
Yeah.
Hello.
Okay, now they're showing up. Good. Okay, this is great. Okay. All right. Let's keep going. Okay. So to talk about this result, what I'd like to do is let me just take a moment to just say what property testing is and how it relates to complexity classes. So we'll fix the size parameter n, and we'll say we'll define a notion of property testing for pairs of functions, which you can equivalent think of as oracles. So imagine you have a pair of functions s and u. These are n-bit functions, so that means they take n bits to 1 bit. And we'll say that a pair of functions has a quantum witness polynomial time query algorithm V if 2 things occur. If one V, the algorithm gets to make controlled queries to both the oracles S and U in superposition, meaning it can ask questions like, does S of X equal 1? And does U of Y equal 1? And they can make these queries in superposition. So they don't just have to make queries to one part at a time. We get to make as many queries as we want. And we have the following property. That the algorithm V is only going to make a polynomial number of queries in total. So we're going to count our complexity by the number of queries that the algorithm V will make. And 2 things hold, that for any pair S and U that are a yes pair, meaning they sit in the set L yes, there exists some state psi, which they could that the verifier could receive, such that V, with access to both these oracles S and U, access to these functions S and U, and the state psi will accept with high probability, say 2/3. And secondly, for every pair of oracles S and U that are the no instances, irrespective of what state psi is sent, the verifier will always accept with the at most probability 1/3, or equivalently reject with probability 2/3. So this is a notion of QMA, because you could imagine the state psi is the state that the Merlin sends to Arthur, and the nice properties that these bullets entail is that Arthur does not have to trust the message, because he can run this algorithm. He's actually able to verify the message, and he doesn't have to trust it. So whenever it's a yes instance, there exists some state that Merlin could send him, and he would be convinced. But in the case it's a no instance, he will never falsely be convinced of a property. So this is what we would mean by a quantum witness polytime query algorithm, is that the number of queries made is polynomial in total, and the witness is quantum. We can contrast this with making a classical witness polytime query algorithm, where now there exists some classical witness that is sent, and it's the exact same definition. And what I won't say in today's lecture, but this is a sort of a known fact, is that if you can find a generic property testing separation, meaning that you can show that there's some property testing problem which can be solved with quantum witnesses that can't be solved with classical witnesses, then you can lift this to proving an oracle separation between the corresponding complexity classes of QMA and QCMA. This part is a standard argument. We won't include it in today's talk. Okay, so with that,
Chinmay, sir, can I ask a very dumb question? I
Please.
sort of missed why. So S and U, they are just essentially indicator functions, I guess, right? This is 0, 1.
They're binary
So
functions. That's right. Yeah.
right. So why do we have two of them? Like I'm sort of missing the intuition, because they're both in either the S instance or the no instance. So for instance, like why couldn't you just take 0, 1 n plus 1 to 0, 1? Is there
Absolutely. You could take the pair of functions, and you could just sandwich them to be one function if you really wanted. That's not important.
but why 2? Why not 3? Like what is the intuition is what I'm missing, I think. Why are we looking at pairs of functions instead of just one function or n k functions? I don't know. Is there some reason why this appears?
There is. The short answer, it's the easiest characterization. But how don't you hold that question for a little bit?
Okay,
It's a good question to have in the back of your mind. But maybe we should first see what the property testing problem will look like. And then once we have that, we can then go on. Okay. So let me present to you a property testing problem, which we call spectral correlation. And once you see this property testing problem, maybe it'll be a little bit more clear, why we're talking about pairs of functions. So we'll do the following. We'll talk a little bit about subsets of 0, 1 to the n, instead of talking about functions. But remember, subsets of 0, 1 to the n are in bijection with functions from 0, 1 to the n to 0, 1, because you can just relate the bijection by membership function, right? So any subset is equivalent to a function. So these pair of functions, S and U, you could also think of as subsets, because you could just mark the one set of them. Okay, great. So imagine the following. Imagine I give you two subsets, S and U, and I draw them in the following picture. Like on the ground, I draw out the subset S within 0, 1 to the n. And that's like, that's the state S drawn here on the bottom. It's like what's on the carpet. And then on the wall, you could imagine I draw out the subset U and I put it on the wall. And then I ask you the following question. I ask you, is there some quantum state, psi, which could have cast both of these shadows? Okay, so what does that mean? It means, well, if I look at the state psi and I measure it in the standard basis, it's going to induce a probability distribution on the Boolean hypercube. right? Because it's an n-qubit state, it induces a probability distribution on the floor. If I measure it in the Hadamard basis, it induces a different probability distribution. And what I'm asking is most of that probability distribution that it generates, is it supported on S? And is it mostly supported on U? Okay. And this is exactly what the question of spectral correlation asks. It says, if I give you two sets S and U, and you optimize over all possible quantum states psi that you could put in the middle, what is the maximum overlap you could get? Right? The overlap is not a binary object, it's actually a measurable thing. And we can call the overlap alpha if it satisfies the equation on the left. Well, the equation on the left is just saying, take psi, measure, see if it's supported on S, apply the Hadamard transform, measure and see if it's supported on U. If that's the case, then it's alpha supported. But the best way to really think about this is that if alpha is a very large number, then morally it says that there exists some state which has these that can cast both of these shadows. And if alpha is a really small number, then it says that no state could simultaneously cast both shadows with good probability. Right? Does that make sense? If you in the audience have seen the cover of the Gödel Escher Bach book, this is sort of the picture you should be kind of having in mind, that the object can cast multiple shadows when viewed from different perspectives. And that's true because these bases are anti-commuting, so the shadows that will be generated are fundamentally different. And so it's a very natural question to ask, because these two shadows sort of are capturing this quantum state by themselves. Neither shadow by itself captures the quantum state, because even if you just give me a set S, there's an exponential number of states that could easily be that could cast that shadow. But this sort of this amusing phenomenon going on, that if you have two of these basis measurements, that there could be you can actually quantify if there exists a state, and it may be the case that no state exists that casts both of these shadows. Make sense? Okay, great. So this problem, if we take it and we construct a computational task out of it, which is very simple, it just says if you're given, it's a property testing question, it's you're given query access or oracle access to these subsets, and all you want to do is you want to decide if the pair are a yes instance, meaning that they are at least some alpha spectrally correlated, or decide if the pair is a no instance, that they're at most beta spectrally correlated. This question is a computational task, and let me argue that it's in QMA. One way to argue it's in QMA is actually to just construct what the proof would look like and what the verification algorithm that Arthur would apply. And what's the construction? Well, Merlin takes the whatever state psi has the generates the spectral correlation that's largest, okay, and he sends over that state psi. Now, what does Arthur do? He uses the oracle to S to measure if the state is supported on S, rejects otherwise. Otherwise, if he has not rejected, he applies the Hadamard transform. He then uses the U oracle to measure if the state is supported on U. If not, rejects otherwise. And his acceptance probability can be quantified exactly by the equation at the bottom. And if you remember back to 2 slides ago, this is actually exactly the definition of spectral correlation, right? So what does this tell me? It tells me that this problem is manifestly in QMA, because if the sets are spectrally correlated, Merlin can send whatever state psi demonstrates the spectral correlation. But if they're not spectrally correlated, the highest he could ever convince Arthur of is, given by some parameter beta. And so as long as alpha and beta are separated by, say, some polynomial fraction, due to standard amplification techniques like Marriott-Watrous or whatnot, you can always lift this to be a QMA algorithm through amplification. Okay, so it's a very natural QMA task, And it's manifestly a natural QMA task because you can see what the witness is. It's this yellow blob for the state psi. It's just the task is described by these classical shadows, and then you're trying to ask if there's some state psi that looks in the middle. And moreover, I'll say that this task of spectral correlation is a property testing version of a natural QMA complete problem. So in some sense, it's the problem you should believe if there does exist a separation between QMA and QCMA, because it's a clean generalization of the hardest problems that are in QMA. I will say more on this near the end of the talk. Okay, so my goal is to convince you that, sorry, this should say spectral correlation. I think it's the typo on Keynote. So my goal is to convince you why spectral correlation is not in QCMA. And let's try to think about how that might go. So let's think about what a classical witness could be. Let's say you wanted to argue a classical witness that Merlin could send over to convince Arthur that two sets are spectrally correlated. What's one thing you could try? Well, a classical witness could attempt at describing the state psi by just describing elements in S, right? Merlin could just start telling you, hey, 0.5 is an S, 0.12 is an S, 0.52 is an S. And that's actually helpful information because if S is in this Goldilocks regime where S is super polynomial but smaller than some exponential, Arthur himself would struggle to find points in S without the assistance of Merlin. This is due to the Grover search lower bound. So he needs Merlin's help to even identify points in S. However, if you are in this Goldilocks regime, then you hit another conundrum, which is that whatever proof Merlin sends by trying to describe S a point at a time will be insufficient because he will only describe the tiniest of fraction of S instead of being able to actually give you an accurate description of the whole set. So in that situation, you can actually prove that if Merlin just sends you a description of a few points in S, that his proof would be insufficient. The only issue with this argument is that we completely ignored the fact that Merlin could send you a proof that depended also on the set U. And the set U is not just some random set, it is a set that is spectrally correlated with S, right? And that may not be a totally random set on its own. So the fact that you have access to both of these is what makes arguing the QCMA problem lower bound so challenging. And let's just take a moment to remark that we actually need both of these sets to have the QMA algorithm, right? So the QMA algorithm relied on having both sets, which were good enough to help us verify that there was only one that to verify the correctness of a witness. But if we had just one of them, then the problem would be outside of QMA as well. I believe you may have heard some of this when Andrew talked about a similar problem a couple weeks ago. Okay. So
sorry, can I ask a quick question about
yeah.
the previous slide? So I think I'm still missing some intuition in general about what is state size. So in the case of pair SU in the yes set, what is state psi should can we give like characterization of like the exact information that this state psi should reveal about S and U? So for instance, maybe I can imagine that if S and U are like some sort of like linear subspaces, then maybe psi just needs to contain some information about the basis. But can we say more like in general for like maybe say arbitrary sets S and U that belong to the yes set, what the state psi should actually contain about these two sets to be a valid witness? Is there a way to characterize this?
No, so that's the best part, right? Is that you shouldn't be able to characterize this, right? Because if we had any classical description of the state psi, that's the entire thing that we're trying to prove. right?
Yeah, but maybe it's even like an exponentially sized description. So I'm just trying to like understand. So I'm not saying like an efficient description. I'm just trying to say like as a state, as a quantum state, what is the actual information that it should capture about SNU to be
Yeah.
a valid witness?
Okay, it should be the top eigenvector of the matrix pi u h tensor n pi s. That's exactly what psi should be, right? It'll be the top eigenvector of this matrix.
I see. Because I'm guessing then you are just trying to like say that there exists some sets S and U that wouldn't have like a very nice, maybe like a lot of structure for which you cannot have a classical witness, right? Is that
Exactly. Yes.
I see. I see.
Okay.
So can I also quickly hop on and
Yeah.
ask one small clarification? So alpha and beta, I suppose you maybe mentioned this already. Is it like enough to take them to be constant apart or something?
You could even take them to be as small as 1 over poly apart. We will end up using alpha and beta that are constant apart.
I see. Okay. Thanks.
Okay. So how might we prove that spectral correlation is not in QCMA? Well, to answer that, maybe the right thing to do is first just take a moment to try to understand a little bit more what make quantum and classical witnesses different. And one delineation between them is that quantum witnesses are used once objects, whereas classical witnesses can be used and reused as many times as you want. To make that formal, think about the following thought experiment. If you're given a quantum witness psi and a quantum circuit V, you can produce exactly one sample from the distribution P. So what is P? It's the distribution when you take psi, apply the circuit V, and measure. You get one sample because the entropic nature of quantum mechanics tells you that you can't pull this back after you've produced the sample. However, if you're given a classical witness and a quantum circuit V, you can produce as many samples as you want from this distribution because you can just run it back as many times as you want. And the crucial reality here is because you can clone the classical witness W as many times as you want, whereas you cannot clone the quantum witness psi. So in this amusing and strange one-line thought experiment, we see that actually classical witnesses appear to be more powerful than quantum witnesses, right? This is a power which you can unlock with classical witnesses that you cannot with quantum witnesses. Nevertheless, I am about to try to argue to you that quantum witnesses are more powerful than classical witnesses. So something in your mind should be buzzing with a contradiction. And what we're going to do is we're going to show that for a certain problem, as long as we can argue that it's hard to produce lots of samples from a distribution, then we will end up finding a contradiction through this procedure, because we will show that it'll be too good to be true for a classical witness to exist for the problem, right? So we're going to say that.
Sorry, I didn't mean to interrupt. But now that I have, I was just so here when you're saying that you cannot clone, right, psi, but a classical thing you can run many times. The obvious thing, of course, is that the classical thing is a special case of the quantum thing, right? So if it is in the computational basis, of course, you can clone it. For instance, things like that, right? So I don't really fully appreciate the contradiction, the apparent contradiction that you're trying to get at.
Oh, yeah, I'm just saying general quantum states can't be cloned.
Right. And if you were guaranteed that it's a classical state, then you could clone it. Classical state meaning then it's just a computational basis state. That's I'm taking like a simple definition of classical. So then you could clone it, obviously, and then your argument was somehow that you couldn't get multiple samples. So you're thinking of some mixed state sort of.
Just wait a bit. Give me a second.
Sorry.
Yeah. No worries. So what I'm going to try to argue is I'm going to argue that there should be a problem for which it should be very hard to produce lots of samples from, but it should be relatively easy to produce one sample from. If I can find such a problem, then I can argue that for this problem that there cannot be a classical witness, but there can be a quantum witness. Because I'm going to provably show that it's hard to produce many samples, so which will knock out classical witnesses. But at the same time, I'll leave it soft enough so that it's doable to produce one sample, which will still ensure that I simultaneously don't prove a QMA contradiction, right? Because I'm trying to prove a problem that's in this strange and esoteric regime where it's in QMA but not in QCMA. So in order to do that, I need something which is going to separate just the information, the classical and quantum information, without breaking the quantum structure itself. So let me say this one more time. So a quantum witness, you can produce one sample. Classical witness, you can produce many samples. So a proof sketch of how you might prove this separation is we identify a distribution for which it is provably hard to produce exponentially many samples from. And then we could argue that if the two classes were equal, we could have then constructed such a sampler, which is a contradiction, right? And if they were not equal, then it would be okay because you could produce one sample because of the quantum witness, but many classical samples would be hard to produce. So in order to do that, I'm going to need to say a few more things, and then we'll get to actually what the sampler looks like and show how this argument kind of follows through. So let me define a notion of a strong instance. So I'll say a strong yes instance is a subset of yes instances from which you can construct a sampler exploiting the differences between your classical and quantum witnesses. And I'll say the following. I'll say that a strong yes instance is a pair S and U, which are at least 59% spectrally correlated. These numbers, 59 and 57, that will come up are just sort of just artifacts of the proof. They're not important. Okay, but we'll say a strong yes instance is a pair that is 59% spectrally correlated, meaning there exists some psi which casts shadows with at least 59% correlation. And it has the amusing property that for any subset delta within S, so you think of S as the shadow on the ground, you pick any subset delta which is small, say size of S over 100 or smaller, we have the property that delta and U together are at most 0.57% spectrally correlated. Okay, so what does this mean? Like, what is this morally saying? It's saying that in order to get that last 2% of spectral correlation, you needed psi to be spread out all over the set S, right? That it couldn't have had most of its concentration for that spectral correlation on a tiny set delta. And so why is this important? Well, this is harking on core ideas in quantum complexity theory of uncertainty principles, right? If you have a very small set delta in one picture, then you must be very uncertain in the other, right? So it's saying that in order to actually generate the correlation between U and S, you couldn't have been very concentrated in a very small region delta. You must have been well spread out. And this is what we'll call a strong yes instance. It's a yes instance for who all the children instances are all no instances. Okay, the children being these tiny delta pairs. And we will need this definition in order to prove our result. And we'll also need a construction of many such strong yes instances, but I can show you later how that comes to be. Okay, so how are we going to prove spectral correlation is not in QCMA? Okay, I'm going to give you 3 theorems, and we're going to spend a little time on this slide, but I hope that after I've written these 3 theorems, you'll be convinced as to a proof technique, and you can go on and this is a good also stopping point for anyone who's like, I kind of understand the high level of this argument and what the problem is. It's a great place to call it quits, especially on a Good Friday like today. Okay, so the first theorem I'm going to prove is I'll prove the following kind of result. Let's take a moment to appreciate it. So what is it saying? It's a complicated theorem, so we'll walk through it line by line together. We'll say that for any V greater than 0, any quantum query algorithm that makes T queries to the oracle U, just T queries to oracle U, no queries to S, that oracle can guess V distinct points in S with probability that's bounded by this term here with respect to the algorithm and the randomness over some distribution. So one way to think about this is the following. Imagine you are the algorithm Arthur, and you are looking at the painting of you on the wall. Okay, imagine you as a painting on the wall. And your task is to drop pins on the carpet in such a way that all V of the pins you drop, they land exactly in the set S. Okay, that's your goal. You want to drop all the pins. And what do we want to do? We want to argue an upper bound on the success probability of such an algorithm. Okay. And right now, you should be looking at me and going, Chinmay, why the hell would I think about this problem? It's completely silly. It's completely made up. Why is this interesting? Hold on to that thought. It's the right thought to be having. Okay. And let me argue to you in just 1 second. But before I do that, let's take one moment to understand what the bound is looking like in theorem 1. The bound is of the following nature. It's polynomial in V and T divided by poly of 2 to the n, right? All raised to the power V. What does that mean? It means the following. As long as the number of points you're trying to find is, say, also polynomial, then we have an exponential term there being raised to the power V, right? So what does that mean? It means that the first guess that you have for finding a point, the first pin Arthur drops, with the probability that it lands is upper bounded by some 1 over exponential, okay? But then it says the following interesting thing is, even if I knew that my first pin landed correctly, my first guess was correct, my next guess is also exponentially unlikely to succeed, right? Because if you plug in V equals 2, you get roughly the square of what you got when you had V equals 1. And then the third pin is also exponentially unlikely. You will keep being exponentially unlikely on sequential results for a very, very long time, right? Meaning that just because you knew that the first pin landed does not help you figure out if the next pin is going to land as well, okay? This is going to be important when we approach our second theorem, which says now let's imagine there had been a QCMA algorithm for spectral correlation, in which case we can show the following result, that there exists a sampler which makes not too many queries, but it produces lots of distinct points from S, okay, with probability that is now lower bounded, okay? And let's look at how this lower bound looks like. So let's imagine that the length of the classical witness and the number of queries are both polynomials. So both Q and T are polynomial functions. Then what this says is that there exists a yes instant, that the sampler algorithm is going to make only polynomially many queries, but it's going to produce probabilities with this following lower bound. And the way you should think about this lower bound is first think about what happens when V equals 1. When V equals 1, you see there's a huge penalty of 2 to the negative Q that you pay. It's a sunk cost. It's the first pin, terrible probability of being correct. But now look at what happens as V goes on, right? As V becomes 2, 3, etc. You see that the probability only decreases by 1 over polynomial with every subsequent query, right? So contrast this with theorem 1, which says that even if I've got my first few guesses right, the next guess is exponentially unlikely. This guy says I'm super unlucky on the first guess, but every subsequent guess is not that much more unlikely, right? It's only 1 over poly unlikely. So if you were to marry this with a distribution over strong guess instances that marries these two theorems together, what you'll do is you'll imply a contradiction once the sampler is asked to produce on the order of Q, where Q is the length of the witness number of samples. Basically, that if you had a sample, if you told me, hey, produce Q samples, right? then we start to hit a contradiction between these two theorems, because the two bounds will pass each other at that point, because one of them is decreasing exponentially fast, right, as v increases, and the other one is only decreasing slower at a polynomial rate. So even though theorem 2 gets a head start in being small, over time theorem 1 will pass it and become a smaller number, which is going to be our contradiction. Okay. Questions about this? Does this make sense?
So
Everyone
the,
sort of under, yeah.
So 2 to the
yeah.
minus qn. Oh, sorry. Just to double check. 2 to the minus qn comes from guessing the weakness. Like
Okay. Yeah. You're too smart for the talk. Just wait a
No, I
second.
just
Yeah.
want like understand
Yeah.
where. Yeah. Sorry.
Yeah. Okay. Yeah.
Then
S and U are randomly sampled here, right?
S and U are going to come from some distribution D, which is going to be a distribution sampled on strong yes instances. Is going to be a distribution I need to construct to marry these two theorems together.
Okay, right. Okay, yeah, sure.
Yeah. One thing to notice, though, is that this the implied contradiction occurs once the number of samples you're asked to produce is on the order of Q, which is the length of the witness. So what is this actually saying? It's saying that the witness morally could only do so much. It could hard code a collection of points in S, right? If the witness had hard coded the first Q points in S, then the first Q guesses based on the witness would totally be correct, right? But then every following guess would be very unlikely, right?
Yeah.
And this is what it's saying. It's saying that there's nothing else the witness could have done but hard code the points. In S, basically the best witness does not rely on the structure between S and U.
Sorry, I think I'm missing a bit the intuition for theorem 1. So, for instance, if S and U are like correlated, it should be possible to do better than this exponential guessing, no? Like, why is it exactly?
It's really the worst case.
But then,
Okay, so that's the most challenging part, right? And it should be the most surprising part, is we're going to argue that no matter what quantum query algorithm that only looks at U can only guess points with this probability. So it's the sheer fact that even though they are correlated with each other, a correlation which is detectable by a quantum witness, it is a correlation that is undetectable by a classical witness. And you are right to assume that it's very hard to prove. Our proof is very long, it takes maybe 40 pages to argue theorem 1.
okay.
It is not any easy result to sort of ascertain. And the rationale as to why it's not easy is because the set U is not random. It depends on S, right? Not all sets are going to be spectrally correlated with S. So the structure of U will leak some information about S. In fact, what you can argue is that if you got to make an exponential number of queries to U, you could actually be very successful at this task, right? Let's notice that if T was an exponential, then the fraction could be as close to 1 as possible, right? Right? When T becomes exponential, the inside fraction could be as high as 1, right?
Yeah.
And
generate.
And then you could guess maybe with near certainty point after point. However, when T is polynomial, you can argue that you can't see much structure. So it's something very interesting. It's saying a few queries to U is not enough to reveal the structure of S. But if you were allowed to make an exponential number of queries, you might find enough structure of S. But this will be sufficient for our purposes because we are trying to separate QMA and QCMA, where the number of queries is restricted to be a polynomial. Okay.
Okay, thank you.
Yeah. So what I'd like to do is I'd like to give some brief sketches as to how these theorems are proven, starting with, I think, the more easy to grasp on, which is this theorem 2, which says whenever you have a QCMA algorithm, you can extract out a sampler algorithm which doesn't make too many queries but produces lots of points in S with good probability. And this sampler algorithm is going to act on the instance S, it's going to be, its success probability is going to be measured over pairs SU, but the success probability is only going to be for sampler algorithms which only query U and have to produce points from S. Okay, so to do that, let me say one thing about the model of the problem. It's you get to make oracle queries, so you're able to access these functions in superposition. So one example is you can talk about query access to S, and you can describe it as the linear extension of this model. Up to Hadamard transform, this is equivalent to this phase oracle model. And for simplicity today, just to and ease of notation, I'm just going to ignore the control bit. So I'll just imagine that your queries are X, then gets knocked on with the phase when you query at U of X. Okay, the full paper has it written with the controlled oracle query. Okay, in which case the query access to the oracle is equivalent to identity minus 2 times the projector onto the set U. And the exact same equation holds for S, that a query to S is equal to identity minus 2 times the projector onto S. Okay? So here's what we're going to argue. We're going to say, assume there exists a QCMA algorithm which has a length Q witness and makes T queries to an oracle S and T queries to the oracle U. We're going to now try to analyze the behavior of this QCMA algorithm on a strong yes instance. Okay, recall that a strong yes instance is any yes instance if delta comma U is a no instance for all the small deltas contained in S. Okay, to do this, what I'll do is I'll first write the QCMA algorithm as an alternation of unitaries with queries to S. Okay. You might be wondering where the queries to U are. What I've done here in this short form is I have imagined those queries to U have been packaged into the unitaries V for now. Okay. Just for shorthand, so the unitaries V are also making queries to U within them, but that won't be important for this part of the talk. So we've just packaged them away for a second. And so here's what on the right here, I've written exactly this alternation once more. And this is running the algorithm on S and U, which is a yes instance, because the queries to U are packaged into the V. Now what I'll do is I'll write down a sequence of states, okay, where I just start replacing these queries to S with identity. So to make it simpler, and at the end of the day, if I look at this sequence of states, I have written here T plus T states. And the last state here, what's special about it? It makes no queries to S at all, right? We've completely deleted all the queries to S. But moreover, one way to look at this is an algorithm which is querying, imagining as if S is the empty set and U is everything, right? This is exactly what this is. It's like querying on the empty set, comma U. And that is going to be a no instance, okay? So the top state in this list is querying on a yes instance, and the bottom state is querying on a no instance. So what do I know? I know that since I have a QCMA algorithm by assumption, that I must be accepting the top state with probability at least 2/3, and I must be rejecting the bottom state with probability at least 2/3. So therefore, the top and bottom states in statistical distance have to be at least 1/3 apart. Right? And as a consequence, this tells me that in this list of T states, there must be a pair whose distance is at least 1/3 times T. Right? This is the hybrid argument. And so let's write this out. We'll say that, look, for some J from 1 to T, the distance between this pair of states is at least 1/3 T. Another way to do that is I could write out the distance this way, subtracting them and using the fact that a lot of the transforms are unitary. And I'll get that the oracle minus identity applied to Vj identity, Vj minus 1 dot dot dot, V1 identity, V0 on the witness W, that's going to be at least 1 over 3t. But what is oracle minus identity? That's just 2 times the projector, right? So now I can show that, look, if I put a pi s on the left side over there instead, I get that this is at least 1 over 6t. So what is this saying? Well, this is saying if I go up to a random j, if I run my query algorithm up to a random j, okay, and I make no queries at all to s, I make whatever queries to u were included in those unitaries of v, I will end up with a state which has at least 1 over 6t support on s, okay? And this is true for this j. So this tells me that if I was to measure, I would have a 1 over 36t squared probability of actually outputting some string that is actually an S. Right? So here's the following basic sampler. It says pick a random j from 1 to t, run the algorithm where we just apply the unitaries vj through v0 and whatever queries to u are required for those, and then measure the query register. This will construct a point x1 that's in S with probability at least 1 over 36t squared. The problem is we would like to construct many points from the set S, right? We want to produce a sampler which produces a lot of points. So we need some technique to argue that we can find a second point that is in S, but that is not equal to x1, because we've already found the point x1. So to do that, what we'll do is we'll run the same algorithm one more time, except this time, what I'll do here is I will switch out the oracle to S for the oracle to the set delta, where delta is all the points I have found so far. Okay, so in this first case, if I found 1 point, I'll imagine delta is just the point x1. The nice thing is that because this is a strong yes instance, even this point, even delta and u together still form a no instance, something I should be rejecting, right? And so I can do this one more time, and I'm still running, and I'll find a no instance. And so here's what we could say is we could lift our algorithm to the following statement. We'll say, look, fix the delta within, which is a subset of S, okay? And now run this sampler algorithm, which already knows a few points in S. And what does it do? It just picks a random query, J, runs the algorithm up to J, except every time it was supposed to query S, it instead queries this delta set instead, and you measure the query register. The same argument will yield that you'll produce a new point that's in S set minus delta with probability 1 over 36t squared. So what does this tell us? It says we've built the following sort of sampler object. It produces multiple samples from S with decent probability as long as SU with some strong yes instance. And does the following. It starts with delta being the empty set, and then for V steps, it runs the basic sampler. Every time it produces a novel new sample, it adds it to its list, and it just runs again. If at any time it produces a repeat sample or it produces a point which isn't in S, it produces a repeat sample, it just aborts and rejects. But what you get is the following property, that each new sample with probability 1 over order t squared is in S conditioned on the previous points being in S. So you have a cumulative probability that all V points are in S is at least 1 over 36t squared, all raised to the power of V. Okay? This is pretty close to where we want to be, except for the fact that this cumulative sampler algorithm is depending upon a witness W. However, as Alex pointed out, one thing we could do is we could, first thing is we could just imagine guessing the witness for this pair, right? Since the witness is only length q bits, if you, sorry?
So I had a small doubt with a basic sampler.
Okay.
So like if you could go back a few slides, like why would sampling J actually work? Because all we are saying is there exists one J for which
Yeah.
the distance is like 1/3t, right?
Yeah.
So, but in the basic sampler, we are essentially like sampling a random J.
Okay, great. So what's the problem? So we can easily make this 1/36t cubed in a very quick argument, which is
Okay.
there's a probability of 1/t of guessing the correct J each time. So that will just give you 1/36t cubed. You can do a little bit more, which is you can argue that not only that it's not that one J is good and all the other J's are bad, the total aggregate success of all of them will give you this. So you can use some like Cauchy-Schwarz crap, and it's not important. But you could bring this up to 1/36t squared. But if you're happy with 1/36t cubed, which I'm also happy with because it won't change anything later on, we're more than happy with this.
Right. Cool. Thank you.
Okay. Yeah. So what you get is that, instead now you can just guess the witness, and you guess the witness at the very beginning of the cumulative sampler. If that witness guess was good, then every future guess after that will, you're going to keep striking gold with good probability, and you'll get that all V samples are in S with probability 2 to the negative Q times 1/36t squared, all raised to the V. Right? So this is exactly what we want, is that, look, our sampler pays a huge penalty on its likelihood of the first guess, right? If you don't guess the witness correctly, it could be terrible for all future guesses. But conditioned on getting that witness correct, the next guesses are all very likely. They're very likely in the sense that there's only 1 over polynomial decay as you go along. This is going to be contrasted with the provable theorem we'll show, which is that no matter what, as you make queries, you should only have an exponentially likelihood, even if you've made a few correct guesses so far, right? So that's and that will be the fundamental difference, is we'll say, is this exact argument that it should be hard to produce many samples, but QCMA suggested that actually all the hardness is baked into the first sample. Right? And morally, this is exactly what is the difference between QMA and QCMA. Right? QMA says every possible copy of the witness is as hard to produce as the previous one. Right? Because every one of them is a quantum state, and a quantum state is really hard to construct. Cloning quantum states is hard. You could only produce witnesses by producing each copy one after another. Whereas QCMA is saying all the difficulty is baked into that first guy. If you can describe that first copy, then because you can clone it, you can produce as many of them as you want. And what is this theorem doing? This theorem is manifesting that to argue that, look, if you have that fact also yields the sampler statement, that you can actually produce lots of samples, not just one sample. Okay, so this is sort of a high-level idea of how we prove theorem 2. One thing you need to do next is you need to construct a distribution over pairs, which is almost entirely supported on strong yes instances. Here's how you could do that. You could construct the distribution in the following way. You could sample a uniformly random multi-set S, which is a set with repeats, okay, of size, say, in this Goldilocks regime, so 2 to the n over 10. We'll pick the uniform superposition over that subset. We'll then calculate like what its Fourier distribution looks like. It's some kind of Fourier distribution. But this is a distribution, and we need to somehow convert this distribution into a set. So what we'll do is we'll sort of include points to be included in U with IID probability based on how heavy it is. Okay, and this will build the set U from all the heavy points in some randomized manner. And what you can show is that if you construct the S and U sets through this procedure, you actually get that the S and U are going to be a strong yes instance with overwhelming probability. Okay, And this is one way you can construct strong yes instances. Having constructed such a distribution, you are now left with the challenge of proving that any quantum query algorithm which makes queries to U cannot guess points in S with too high a probability. This will end up being the central challenge, is proving such a sampler statement. And in fact, the follow-up work by Bostanchi, Huang, and Vaikuntanathan, what it does is it constructs a similar sort of exponentially decaying sampling upper bound for sampling from some quantum error correcting code. Okay, so that result takes inspiration from this one and constructs this sampling upper bound through this procedure. High level idea is that we're going to prove our sampling upper bound strategy through the following few things. Is we sample the set S and U from this distribution by first sampling a uniformly random multiset and then sampling the corresponding U. What we'll need to do in order to prove this probability upper bound is we're going to have to employ some fancy tools, which will be the compressed oracle technique for understanding what queries to this distribution look like. And the way we think about that is, look, if we're trying to measure the success of our algorithm over the distribution D, it is mathematically equivalent to study the success of the algorithm, not over the distribution D, but over any purification of the distribution D, and we analyze running the algorithm with respect to this superposition. Right? The nice thing is that the purification of this distribution has a very natural interpretation. In particular, since the set S is sampled by sampling a uniformly random multiset, and this is the crucial reason why we use a multiset, is that the purification can be naturally expressed in terms of bosons. And then all that's left is to argue that every time I make a query to the oracle U, the query over the randomness in U also has a bosonic interpretation. Marry those results together, and we argue a probability upper bound by arguing that anytime you make guesses, that is mathematically equivalent to an annihilation operator in the bosonic framework, and anytime you make a query to U, that is equivalent to applying what's called a hopping operator. Then argue that it requires a lot of applications of hopping operators to actually have any success on the annihilation operators. We are able to prove our result. However, this is a very challenging task, and in the interest of time, I am not going to talk about any of this third part of the paper. And let me just go on to say a little bit about what lessons you should take away from this result.
So can I just ask one quick question about the step one in the proof you were mentioning?
Yeah.
So basically there you need to use like the compressed oracle to record queries to you, right? Because
yes.
you are querying you to find out some information about this. But if I remember correctly, you're saying that S is the uniformly sampled function, and U is given by some distribution that would, I guess, be somehow parameterized by S. So, but I feel like in general, like we know very well how to use like the compressed oracle for like uniformly random functions. So it also means you have to like generalize the compressed oracle for this more special distribution of U that you are considering, or how should I?
Yeah, exactly. It was a real challenge to understand what do queries to you look like. Like, what do they operationally mean? What sort of information are they telling you? One way to think about them is that the position and momentum analog, which is the same as like standard versus Hadamard basis, suggests the following: is that if S is we can think of this, since S is in the standard basis, we could think of it as sort of the position system of a bosonic system. The queries to U tell me something about the momentum of the corresponding bosons. They're measurements of momentum operators. The idea is that initially a set S since it's uniformly random, it's like the bosons are in uniformly random positions. But if they're in uniformly random positions, that's effectively like saying that they all have momentum 0. So you sort of start off in a world where all the bosons live in the space of what we call a condensate, which is all the bosons are basically in the 0 momentum mode. A few of them have been knocked out. And then what you try to argue is that you argue that as you make queries to U, the overall purification of the system maintains this invariant that it's mostly all the bosons in momentum 0, and that invariant doesn't change too much over time. That's not exactly correct. You can actually argue that the invariant you need is some notion of what's called quasi-evenness, which is a little bit more complicated. But you can argue that as long as you have that the purification at the very beginning, it's all the bosons are in the 0 momentum mode, then you argue the following results, that after T queries, the post-query state is very close to being a condensate for a small number, okay? And after T queries, the probability that it's not quasi-even is also exponentially unlikely. You can put these two results together to actually argue your bound, which is to say that, you know, there's some invariant preserved, which is this quasi-even condensateness. And from that invariant that's preserved, I'm able to prove my sampling probability upper bound. But perhaps I'll leave this for another talk some other day.
Maybe this is like a silly question, but wouldn't it have helped to first sample U uniformly at random and then have S defined as a function based on U, so that you still have like the compressed oracle with respect to like a random function, and then you're trying to find out some information that is related to this S, or no?
Yes, that would have been great. Unfortunately, that will not work. I can say why. If you pick a uniformly random set U, in fact, you can argue that there is no small set S, that is sub-constant size for which U is spectrally correlated with. So a random set U is never spectrally correlated with a small set S. And you need a small set S to make this sampling out argument work, because you need it to be hard to produce samples from. So you need S to be at least small enough that, you know, it's not, otherwise a randomized algorithm could produce samples from it. So unfortunately, that would be great if you could argue that, you know, queries to U is uniformly random, that then you could still do the same thing for S, but for uniformly random U, there just doesn't exist in S. So these instances which are spectrally correlated are structured. The idea has to be that the structure is not something that is discernible in polynomial time, right? And that's what you're going to need for the sampling algorithm. So to conclude, let me just say the following. What we can argue through this, you know, rough sketch is that QCMA algorithms cannot calculate spectral correlation to even constant accuracy with only given oracle access to the set S and U. A result by Henry Ma and Anandarajan shows that it's QMA complete to compute spectral correlation to 1 over poly accuracy when the sets S and U are now not just given by property testing functions, but they're actually solution sets to 6 local CSPs. Okay, so what they did here is they took the Feynman-Kitaev clock construction and they looked at it through the framework of spectral correlation, and they proved that really the Feynman-Kitaev problem is really some problem about spectral correlation. Okay, and what does this say? It says that, you know, this property testing problem that we have shown this separation for, it actually has a significant lesson that is worth understanding. And this is saying that if QCMA equaled QMA, then the QCMA algorithm would have to be able to solve this QMA complete problem, right? And therefore, the QCMA algorithm must depend on the structure of the CSPs that define this spectral correlation question, right? Because if they didn't depend on the structure of the of the CSPs, then it would break the result that we've just proven here, which is for unstructured sets S and U. Okay? And this you should see as the analog of the search oracle separating BQP and NP, right? The BBBV result that proves that BQP should not be able to calculate problems in NP with respect to an oracle. What does it say? It says, look, it doesn't say that BQP does not solve NP. It says that any BQP algorithm for an NP complete problem, it must depend on the structure of the CSP that it's trying to solve. It could not be something that is just unstructured black box way of solving NP complete problems using quantum, right? In the same way, we're saying QCMA algorithm, if it was to solve QMA problems, it must depend on the structure of the CSPs now, because now there are two CSPs, and it cannot just black box solve the question. And it produces a significant barrier for understanding, for proving that QCMA equals QMA, because we don't know how to capitalize on the structure of the CSPs and the fact that they're spectrally correlated to actually construct a witness. And in this regard, I think this oracle result is really special, because while it is very challenging to prove this result about the bosons, the lesson at the end of the oracle, the pot of gold at the end, is I think worth the wait, because now we have some serious limitation on why QCMA cannot prove QMA, because we don't understand what the structure of the CSPs look like for spectrally correlated instances. Another way of thinking about this is if you're familiar with like XXZZ Hamiltonians, in order to be a yes instance of that Hamiltonian, there has to be some elaborate dance between the X-type Hamiltonians and the Z-type Hamiltonians that allows for constructive interference and complex superposition. Right? Destructive interference and complex superposition. Right? That's really necessary. And it's saying that, look, that we have to exploit this in order to construct a QCMA algorithm. So there's some significant barrier that's been imposed due to this oracle separation as a consequence. So there's some open questions. The second one of the separation being extended for BQP with advice and BQP with classical advice has been shown. But there are lots of other problems which have been proven in prior work with respect to quantum oracles that we could now think of in terms of classical oracles. One intriguing question I think that's really worth thinking about is, what's the best quantum algorithm for spectral correlation? Is there a good quantum algorithm for this test, since it's complete and since it's also hard for QCMA? And now that we have this task which separates QCMA and QMA, it actually also does more. It separates clonable QMA from QMA. Are there new cryptographic primitives that are worth generating that can be generated through this spectral correlation framework? And lastly, does this analysis give us any insight on the Aronson and Binus conjecture, which has been related to the QMA-QCMA problem through prior works? And we can maybe now that we've solved this result, can we go back and see if it gives us any insight on that particular question? Okay, with that, I will end. And yeah, thanks for inviting me today.